So this is the last session of this year's XLDB, and I hope you all go back with good memories of XLDB in your long-term storage. This session is about long-term storage, and we have two excellent speakers. Tina Carter here from SLAC is the computing coordinator for the BABAR experiment and manager of offline computing for the super CDMS experiment that's looking for dark matter in cryogenic places. It's the high energy physics. Actually, both of these speakers have much better naming than any of the astrophysicists. We just have terrible acronyms. But and then we will then follow this up with Henry Zhang, who's the senior product manager from AWS, Amazon Web Services for Glacier, their long-term storage solution, and he's also a graduate of Stanford and happy to be back here. So let's start with Tina.
Yeah, hello, I'm Tina. Okay, sorry, I was having fun. This is a representation of events from the BABAR experiments. So, and I'll give the reference for this little toy later. So let's start. Okay. So first of all, a little introduction about BABAR. The aim of the experiment is to study the difference between matter and antimatter, and why this difference exists in the first place. The stable matter, the one that we touch every day, is actually made of a very small subset of all the particles in what we call the standard model. All the other particles are actually produced in cosmological events at Big Bang, or we can use particle accelerators. And the size of this asymmetry, if you want, is given by just one extra particle produced every 10 billion particle-antiparticle pairs. So that's all that amounts to the visible matter that we have in the universe. SLAC, the LINAC, SLAC, and PEP2, there is a linear collider, and the electrons and positrons produced by the LINAC are accumulated in the PEP2 rings and then smashed together in one point where the detector used to be. So this is BABAR, is a 1,200-ton general-purpose detector. General purpose means that we want to look at everything that happens inside, and we try to make it as close as possible, hermetic, so that we can observe everything. This is, for example, how it looks inside one of the events. This could be one of the events that were playing music before, for example. The experiment operated from October 1999 through April 2008, and we collected billions of physics events, each corresponding to a plus, E minus annihilation process. And the energy at which they annihilated is a resonance, a particle, if you want, called upsilon-4s, which is really a quark B, an anti-quark B bound state. So the final data set of BABAR contains over 9 billion physics events and 27 billion simulated events collected in 1.6 million of files, and they altogether are about 2.7 petabytes. Overall, the experiment, though, produced 6 petabytes of data. Of course, we cannot bring forward all these petabytes, so we are only working on the latest data processing. This is who we are, the BABAR collaboration. Right now, we have 270 members from 76 institutions in 13 countries. Plus, there are a number of associates, which can be computing people or students also. The BABAR physics program is extremely wide. That goes from the nature of matter and antimatter, and also the properties and of interactions of quarks and leptons, and also some new physics like dark matter and light Higgs searches. The wealth of physics coming from BABAR is huge. These are only some of the results of the last years. I won't go through them all, don't worry. Also, the B factories, which is BABAR and our Japanese counterpart, Bell, helped establishing the symmetry breaking, so what we call CP violation. And this basically was the reason for the Nobel Prize to Kobayashi and Mascava in 2008. We published more than 550 papers, and we still have tens of analyses aiming to publication in next years. But we have also very limited funding and support. So the BABAR data will not be superseded by the LHC experiments. They are of different kind. But we try to match our data preservation with the Bell 2 schedule, which is the upgrade of the old Bell experiment, our counterpart. And, but even so, some data sets are expected to remain unique for a longer time. These are other upsilon kind of resonances. According to their schedule, Bell 2 will come online around 2018. So that is what we are aiming for as a minimum target for preservation. So what we have is the long-term data access project, which is dedicated to the preservation of BABAR data access, the computing environment, at least until 2018. This may be adjusted depending on Bell 2 schedule. We know they are a bit late, so we are now aiming for 2020 if possible. And we want to provide support for data, code, repositories, databases, documentation, storage, and also provide CPU capacity for the physicists. So here is where virtualization comes to the rescue. We enclose the BABAR analysis framework into a frozen environment. We don't freeze the framework itself, so that we can keep all the potential of our analysis framework, including discovery potential, so discoveries of new particles, for example. This is simpler to maintain from the documentation point of view, and also to provide support for the users. We mostly use open formats, like root for the data, MySQL for the databases. The code is written in C++, object-oriented, Tcode, Perl, Python. The data management and distribution is done via XROOTD, which provides a transparent way to access data, whether it's on disk, tape, or network, it doesn't matter. This will help us to minimize the effort needed to maintain the system. For example, tools validation and upgrades. Every time a platform changes, we have to validate and verify that our tools still produce the same physics result, so that our results are not depending on the platform, for example. Still, it's very complicated to keep everything together and working. So the central element of the long-term data access project is an integrated cluster of computation and storage resources. We use virtualization a lot to ensure the continued operation of our framework. And also we use some distributed technique for scalability. Okay, these are just the real ingredients of the cluster, so I won't go into much detail. So what we are looking for is a simple, unique solution in which we mix CPU and storage resources on the same node. So each machine is basically a simple building block for the whole cluster that overall has to have standalone capacity. As long as it has power, it will be able to run and provide resources for the analysis. The design is scalable and portable, so it's an all-inclusive design that can be reproduced at any scale in any of our collaborating institutions if they want to. There is security and flexibility because it's stable against disk or node losses. There is lots of redundancy in the system. And also, we use lots of back version elements because we are preserving the old environment. We'll see how this works. And it's completely on demand. The users choose what they want from the system. Overall, we have 1.2 petabytes of XROOTD-based storage for physics data, 64 terabytes of ZFS-based storage for the user data, 3.5 terabytes of RAM overall, 1,600 job slots, and we support SL4, SL6, SL5, and SL6 platforms. So this is how the network is organized. We basically have a single point of access for the users, which is a login pool. It's a load-balanced pool. And three subnets. The login, where the machines are attached for login only. Then we have a subnet that we call for the servers, which is the infrastructure, basically, and one subnet for the virtual machines. So on the infrastructure network, we basically have everything that we need to make things run. So we have the batch server, for example. We have the identification services and the network services, databases, NFS servers, and a test server. Then there are the batch servers, which provide disk for the local XROOTD cluster that distributes the data across all the user applications, and also provide cores to run the virtual machines. So while the hypervisor is connected to the server subnet, the virtual machines are actually connected to the virtual machine network, subnetwork, and are separated by the rest of the system through firewall rules implemented in the router. So this is how it looks overall. We have 54 of these machines which have large disk space, and we have 20 machines that only provide CPU resources. So virtualization security. Of course, using a virtual machine solves the problem for us of the system administration, because we just have to manage a few images, while the physical hosts are centrally managed by the SLAC compute division. So this does not weigh on our shoulders. But we have a security threat associated to a virtual machine connected to a network running an old operating system. So we take a risk-based approach. We assume that all the frozen, outdated systems that can be compromised are compromised. So we prevent modification or deletion of the data, including any modification that would allow system outside of the LTDA, so SLAC in the first place, to be compromised. And the isolation is basically implemented via firewall. The virtual machines are created on demand through the user request. They submit a job, and a virtual machine is created as a response. And to avoid that a compromised system can reach outside the system, the LTDA, basically we do not allow persistency. So basically, any change to the virtual machine is written on a temporary file that is deleted when the virtual machine is shut down. So the firewall rules, basically the virtual machines are not allowed to connect to the SLAC network or the world. We allow one-way SSH from the login machines into the VM network. So you can enter the system, but you cannot get out. And there is only a very well-defined number of services that can be shared between the virtual machine network and the service network. Because, of course, we have to provide the data, first of all, to the virtual machines to run their jobs and analyze the data. And we have to provide identification of the users. What we use as a batch system is Torque, and MAUI is the batch scheduler. We moved away from Condor and Nimbus because they were extremely unstable for us. The same happened with libvirt. We now use QEMU directly. libvirt used to crash several times a day, actually, so it was really, really painful. The resources in the system, each batch server has 12 physical cores. We actually use hyperthreading, so they're the double, of which one is dedicated to the host itself and to run XROOTD, and the other 11, which provide 22 logical cores, run virtual machines. So each server basically runs 22 virtual machines, each corresponding to a batch slot. Each batch server has 24 terabytes with no RAID. We don't really need that. We just maximize the usable space because all data is recoverable for tape. And one disk is dedicated as a scratch for the copy and write of the virtual machines. This is how the job submission works. So basically, the prologues and the epilogues of PBS are used to create and destroy the virtual machines. And also, they create the network interface for the virtual machine to the system. It's a very, actually, simple system. The user just submits a job, whatever it is, and then the PBS server collects the job and creates a little script that will restore entirely the environment that the user has in his home directory in the login machines. With this, the prologue scripts create the network interface for the virtual machine, and then it creates a virtual machines with the parameters specified through the script. The virtual machine is booted, runs the job, quits, and the epilogue script collects the output and delivers it to the user. All virtual machines actually are associated to a MAC address, which is defined per host, and we use a little local DB to keep track of everything. We also looked a little bit to the performance. For example, we compared our virtual machines with the SLAC batch queue. So we used RHEL 5 and RHEL 6 as terms of comparison. So with hyper turning off, our machines were slightly faster, but then when we turn hyper turning on, of course, we get a bit slower. But on SL6 was amazing, faster than SL5. SL is a scientific Linux. You can think it as a Red Hat 5 or 6. But then it's faster by 35% CPU time and 50% wall time overall. We also looked at the I/O performance of the whole system for XROOTD to look how fast we could deliver the data to the jobs. And turns out that basically we could grow the system 5 times larger and would still be OK. Memory usage, we switched to using KSM, and this drastically reduced the amount of RAM needed for the jobs. So this was very effective, especially because we use lots of identical processes, which are the VMs. Problems and solutions, we faced lots of unexpected problems, and we found solutions. So for example, a couple of times, updates would disrupt the system very badly. For example, these are the two worst that happened. The virtual machines were created, but they were not reachable, or we could not log in into the system. So after that, we implemented a validation system that allows to test the updates before delivering them to our hosts. So we have a test server that validates and releases the list of updates that are allowed. To make things simpler, we removed all not essential software packages so that the list of updates is very small. There was also, at the beginning, an intrinsic dependency between the services running on different machines, like NFS exports, home directories, working areas. So it was very difficult in the beginning to put the whole system together after an outage, for example. We removed all the dependencies, and now the system can boot on its own without any help. We also have a monitoring system which checks the system, the disks, the connectivity, the services, collects job statistics, and puts everything on the web for us to check. In case of problems, email alerts are generated. Stability. So the cluster now is able to run for long periods of time, I mean weeks or months even, without any human intervention. and it's able to recover even from complete outages with minimal or no human help. So, for example, there are periodical reboots of the machines when updates are delivered. It all happens automatically. We don't even check that this happens anymore. And if there is a problem, email alerts will come in. We also have a small version of BABAR. We call it BABAR to go. We build lightweight virtual machines for each used platform with the latest code release included that can run under the most common virtual machine players, be it VirtualBox, VMware, whatever. We just need to add the data, which is a bit of a problem. But XROOTD comes to help in this case. We created a XROOTD Federation, which is the on-demand sharing of all BABAR data among the collaborating institutions, the ones that want to join the federation. It's very similar to what Atlas and CMS at CERN already have. It's very similar, actually. Test installations are ready at SLAC, at Gridka in Germany, and other BABAR institutions that volunteered. The installation package is ready and very easy to use. It also provides a basic monitoring for the local installation. The requirements are actually extremely lightweight. We just need a small Linux machine with a few hundreds of gigabytes or a terabyte. The installation package, we made a video. It takes exactly 2 minutes time to install. Little or no manpower is needed. Just make sure that the machine is up and connected to the network. So we asked everybody in the collaboration that has a simple desktop sitting in their room doing not much to just volunteer and run this thing. What we found very difficult was to go through the university's firewalls, but that's another story. So all BABAR data are distributed among BABAR institutions. Some data are at all institutions, though, like the conditions files, because they are needed for each and every job. But no whole scheme, physics schemes are in a single place. A scheme is just a pre-selected kind of physics events so that people don't have to go through the whole data set, through the whole 2 petabytes of data to find the events they are interested in. But since we don't want to hit a single institution with hundreds or thousands of jobs, this is a requirement. Jobs or the users don't need to know where the data are sitting. Jobs can simply access the data files instantly, like always before. It's just completely transparent to the user. Of course, all data files have to be distributed redundantly in the cluster so that not one single institution is hit at one time for requests. And also, there is no need for RAID. We have tape backups for the data. And XROOTD can reallocate the data when it's needed, where it's needed. One piece is extremely important is the documentation. So all the most used and fundamental information has been checked, updated, and moved to a MediaWiki server. We call it the BABAR Wiki. All pages in HTML format are marked but kept online for archival. Pages that are supposedly never to change again, they're left in their original location for historical reasons. The wiki pages undergo a collaboration-wide review, much like the papers that we publish do. And experts sign off on the content of the migrated or updated pages. There is a documentation working group, and their members, they act as moderators to avoid duplication of information and cross-references, so to keep things in check. Pages are reviewed periodically. For example, we have a workbook, which is a step-by-step tutorial from the login to the final root tuples analysis, and technical pages also. We also have personal pages and notebooks where users can basically show plots, make to-do lists, just their day-to-day workbook. And we tested the solidity of the documentation using new users. Whenever a new student was coming in, just, okay, this is your starting point. Let's see how far you go and discover the bugs and the flaws in the documentation. It was a bit nasty at the beginning. But So on the long term, we're basically moving toward a new operating model in which all the services that are now running on physical hardware will soon run on virtual machines. This will enable us to make the services available beyond the lifetime of the hardware. OpenStack is being adopted as SLAC, and I hope that this could open a number of possibilities for our virtual machines in the future. Tapes, we are currently using 2.7 petabytes of tapes to store the data. This raw data plus the latest 2 data processing cycles, which are the ones that people are still using for their analysis. The data is stored on storage tech T10K-B tapes. SLAC migrated a few years back to T10K-C, and we are now looking forward to T10K-D migration. These are physically the same media as T10K-C, just reformatted for more capacity. So the oldest data at this point, since our finances allowed only to buy the equivalent of 2 petabytes of data, we have to make a choice, and the oldest data will not be migrated. It will eventually be dropped, also because this corresponds to analysis that will come to an end, that will be published, and this data will not be useful anymore. So let's go a little further beyond BABAR only. DPHAP is the Data Preservation in Energy Physics. It was born as a study group and is now a full-fledged collaboration. You can visit these links to know more about it. They work toward what is called Horizon 2020, which is a European funding program, a huge one for 80 billion euros, I believe. And among the project in Horizon 2020, there is also data preservation. So lots of groups in energy physics are targeting funds in this program. Of course, data is not just bits, it's more than that. There is the data, but there is also the software with the environment to keep it alive. And there's the documentation. If you don't preserve all of it, then the data is just bits on a tape and has no life, no meaning. Other parameters that can prompt for preservation are, for example, the use cases and the target communities. For example, new analysis or cross-checks of new discoveries. Now, the larger experiments are only at CERN. What if they discover something and no one else can cross-check what they discovered, for example? And then there is education and outreach. All the data, like BABAR data, for example, even though it's still producing lots of physics results, is data that is very well understood and is a very good place for students where to learn. Then there are other things that we can evaluate, like uniqueness, reuse, and then also make it open to the public. So the future of data preservation is in the data storage itself. In energy physics, generally the primary copy is on tape. BABAR data are stored at SLAC, and a second copy is hosted at CCN2P3 in France. We need to migrate to new media about every 5 years or so. The new medias are usually more efficient, reliable, but not necessarily less expensive. So it depends. So for how long this can go on, a decade or two perhaps, but I don't expect more than that. And then we have to face what comes next if we want to preserve the data. The software environment, virtualization, of course, has proved its worth, but is also evolving and it's changing. And what happens if we face a disruptive change in the next 10 years or so? So these are all problems and questions that we need to find an answer to. Documentation is pretty much well settled on wikis and HTML plain files. Well, you know, physics is not scale invariant, and in more than one way, it's not just the physics itself, it's also the fundings, for example. These are some projections for the CERN data, for example. So they will basically go to the exabyte range around 2020. The cost will also increase. Here, I think the yellow bars are the new data, and the orange ones is the cost for the carryover of the old data. Overall, the CERN grid system has 500 petabytes of storage distributed in about 170 sites in 40 countries. So it's a huge system. So my problem today is to preserve 2 petabytes, but what will happen when the other experiments will have to preserve an exabyte? Will it still be difficult for us to preserve 2 petabytes? I think it will not. Today, for example, the previous generation of LHC, which is the LEP experiments, they do not pose a problem anymore. They're so small in comparison, which is really nothing. Anyway, so thanks. This is the list of people that more directly worked on the LTDA. Some of them are actually in this room. And this is the wind chime, the thing that you listened to before. It was a Science Hack Day here in San Francisco a few years back. Matt is one of our collaborators, went to the event and had fun with the music. If you want to discover more sounds, just go to his website. Thank you.
So where do you see the role of container technology in what you're doing so far? I mean, virtualization is sort of heavy at some level and was a good, or is a good technology, but
Yeah.
Moving forward, do you see a role?
A way forward.
Yeah.
Well, forward, how long in time? I mean, the question is, how long is long term? If you ask a physicist, the answer is forever. If you ask to our computing division, they will tell me, like, is 3 or 5 years enough? So virtualization is a solution now. It will be probably a solution again in 10 years. I have no idea afterwards.
And is this, I didn't get a good sense of how you manage your users changing sort of the software layer for their flavor of the virtual machine, or is this one sanctioned virtual machine that everybody uses, or can they bring in their own code? And
so the problem that we have to face is extremely simple because it's one thing. It is one thing. Our virtual machines have to do one thing, that is to run our framework. Users can develop their code within the framework. It will plug in absolutely naturally without any problem. Then, if they want, they can take away one of these virtual machines. They have root access. They can do whatever they want. But fundamentally, the problem is to run a BABAR environment. It's extremely simple. That's why when implementing the cluster, we try to dumb it down as much as possible. The less things you have to worry about, the less things can go wrong.
so the assumption is that whatever computational resources they need are within the VM framework. They're not going to say, I need 16 of them connected and I want to work on something that is...
Oh yes, there are enough resources for them to do so. Absolutely. They can run on the whole data set within 1 day or so.
But the single virtual machine, if they need more RAM or more CPU, is that something that's constrained, or like is there like one size fits all, or?
Well, no, there is a certain flexibility. They can parallelize the jobs if this helps. So, they can make requests if they need more RAM. There are a number of things they can do.
Oh, okay. Thank you.
I had a question along sort of the same lines. Because you've chosen to freeze the environment, that means that you don't have to maintain the original analysis software. You don't have to port it or improve it at all.
No, that's the contrary. We freeze the environment, but not the framework. The framework can be still modified. You can, for example, if someone comes along with a new physics model, and we need Monte Carlo simulation to describe the physics model, we can actually add another generator. and run a simulation.
But it has to be done within the frozen environment.
Within the frozen environment.
Which means that people have to use the tool chains and the tools that are available only in that environment.
Yes. Unless you have time and develop your own new tools, yes.
Right.
Freezing the environment means, for example, that we don't have to validate the physics result every time a new glibc comes along. Because, for example, a glibc change can crash the jobs, can change the outcome of a physics result at runtime. So what I'm avoiding here is to having to validate the software over and over and over again.
Right, but we have people that are, complaining now that they can't use all the whiz-bang C++ 14 features and things like that. So you must
that's
have
what we get
similar
when the
kinds of
support
things.
goes down, when the founding goes down. So if people have time and they want to play with these things, they're welcome to. We try to help, but within the limited resources that we have.
Is there a correlation between the mass of the collider and the mass of the infrastructure to manage the data it produces? And if so, have you picked a Greek letter to describe the constant?
No. So, no, it's, the PIEP at a certain point, they thought that half FTE would be enough to support the experiments, but no, that's not the case. There is always some user that comes along, I forgot my password, I don't know how to do this, I forgot. It's just, nah. It's just crazy.
So in the long term, there will be a moment where you have to decide how much physics you do with this amount of data. And eventually you will need to put it somewhere, right? So like 3 years ago, there were presentations about data curation and preservation from the Library of Congress. Do you have any experience on experiments sending the data there for a long-term custodial?
Well, so there is a mandate from the DOE to preserve the data as much as possible, but there is no funding. The real mandate is to make the results open to the public, available to the public, which we do. In energy physics, all the results are public, basically. Again, you can store the data, but if you don't store the documentation and some way to keep alive the environment, they're just bits on a media that mean nothing. So the data has to be alive to be meaningful. That said, I've never tried. They don't have so much space anyway.
Okay, thank you very much.